general discussion session, and I'd like to ask all the morning speakers maybe to come here and sit down on the chair. You can stand. And the chair of this session is Hans-Thomas Eize from Pisa.
Thank you very much. Hello? That's the first speaker. Okay, let's start right away since we are rather restricted in time. I want to open this with just paraphrasing Professor Haldane, two general remarks he made. First one was saying controversy is good for innovation, which I really like. And the second one was in his concluding remarks that he said in 100 years we did not change quantum mechanics, or rather one should say quantum theory. And so my question to the four speakers is to just give a personal statement, just out of my own curiosity, how they feel about the next 100 years. Will we change quantum theory or will it stay like this? Of course, it's speculative, unfair, and everything, and you should not use much time for this, but I'm personally curious to learn their opinion about this, and then we open the floor to technical questions. Please.
Well, I'll just say that I think there's no going back. I think quantum mechanics will evolve, will introduce different concepts, and may change so much that we will hardly recognize it. I think the empirical and conceptual basis is so deep that we'll be building on.
I think it's off, yeah.
Yeah, I think, for example, we'll probably understand a lot more, probably less than 100 years from now, about multi-particle quantum and deeper understanding of what we can do with multi-particle. And I think we're going to learn how to control states and do interesting things that we probably can't dream of right now. But we won't change. I don't think we'll change the. Who knows? But I don't think we'll change any of the basic laws of quantum mechanics. Maybe we will.
Yes, I mean, for me, quantum physics is relativistic quantum field theory by now, and so this theory so far exhibits no inconsistency, either experimental, and there are infinite number of tests for this theory, or theoretical. And usually when theory requires some reparation or extension, usually theory signals about it somewhere. And we don't have such things in quantum field theory. I mean, of course, there are domains where calculability is restricted, for sure. I mean, very high loops, we have to go to resurgence and this kind of stuff, but there is no signal anywhere that quantum theory fails. Of course, it may develop in the sense that we may get some more efficient ways to calculate, or we should wait for some signal which tells us that, okay, we need some further extension. And I'm not aware of anything like that so far, including gravity, including string theory, or black holes and stuff like this. I think quantum theory so far is perfectly fine.
So I will answer with briefly. I organized a public lecture at my university about 10 years ago. It was the time of the discovery of the Higgs particle. And there were a lot of distinguished physicists. I was just chairing the session. And one of them was George Sudarshan, who invented the D-8 theory. And one young person of the audience asked, Professor Sudarshan, why do we have a Higgs particle? And Sudarshan said, young man, don't ask me why Higgs, ask me why the muon. this made me think about, I mean, this is the previous generation of physicists, and I think that at that time they were thinking about, there was the electron, and then suddenly there was the neuron too. And a lot of people did not understand that. So my feeling is that things will change quite a bit in quantum theory. But I'm not the most, how can I say, there are people who are much more entitled to answer this question than me at this stage.
What do I do with this?
I guess you're not probably give an interesting answer.
We can also, if we want to extrapolate, we should consider what we're extrapolating from. And I think if we consider it the way quantum mechanics was in 1925, it's true in a sense to say it hasn't changed, but it has changed in very significant ways. The framework, the very broad framework hasn't changed, but it's now not just a framework, but an actual, not just a frame, but an actual rich picture of exactly how the world works. That's very, very powerful. And some things have changed. I would point in particular to the understanding of quantum statistics, that we really have radically changed our understanding of that very basic feature of quantum theory. We know that there are more general possibilities than were originally envisaged, and why.
Maybe I can comment about the Higgs discovery. Actually, Higgs discovery is precisely the triumph of quantum field theory. We knew that either there should be a Higgs there, a Higgs field, a new degree of freedom, or something even more exotic, and because of unitarity. So the standard model without the Higgs particle has problems with unitarity, around 700 something GeV. So the Higgs prediction is actually a triumph precisely of quantum theory. In that, I don't think it's the same level as muon, because standard model with one generation is a perfectly consistent theory. There is no theoretical need, at least not the one we understand, for a muon. But for the Higgs, for sure. So therefore, it's a very good example.
Okay, maybe if there are no further comments, I think we should open to questions from this audience, please. Please.
Okay, I have two questions, but they are closely related. So, if quantum theory is fine, it is fine because everything we see in the experiment is agreeing with it. Of course, quantum theory breaks our intuition, definitely. That I think we all agree, even after 100 years, it breaks our intuition. Are we doing experiments that challenge quantum theory? That's one question. Another thing somewhat related to what Professor Haldane mentioned, some of the works of Dvali and Keating involve understanding of quantum chaos, instabilities like inverted harmonic oscillator like instabilities in quantum Hall effect. I feel that these are challenges, but I do not know if we are doing any experiments to address these challenges.
Well, if you try and propose a good experiment to show it, I mean, yeah, you need to come up with experiments that test quantum mechanics on presumably entanglement on larger and larger scales. But so far there's no indication it's breaking down.
Yeah, I think, well, every experiment is a test of quantum mechanics. But if you ask where quantum mechanics hasn't been stress tested yet, I think the effort to build and scale up quantum computers is one. I know Professor Hooft has doubts about whether that can be done. And I think another is testing the interface between quantum mechanics and gravity, where rather little has been done experimentally.
Can you comment on quantum chaos?
I think quantum chaos is just another chapter of quantum theory. So I would be very surprised if anything fundamental came out of that.
Okay, next question, please.
Hi. Yeah, I also have a somewhat speculative question to all on the panel, which is, what are your perspectives for the interpretation of quantum mechanics? If we haven't tested a lot of, I mean, what do you think will be the future of the interpretation of quantum mechanics?
Get used to it.
Well, I mean, on a personal level, most of us probably believe we have free will and do things. That's one of the issues that people talk about philosophically in quantum mechanics. Is everything's okay since the beginning of the universe. But, you know, these things are kind of very, you know, how we live our lives is clearly not. We assume classical physics in our perception of world reality.
Well, I'm sure you're not sort of that there's a contradiction. It's that we're coming to understand how emerging from quantum mechanics there can be a perception of classicality by participants in the wave function under the right circumstances. I think it would be very good to make that more rigorous, finding percipient emergent objects inside quantum mechanical wave functions, but I think it's a technical problem, not of principle.
Can I say something? So I also think that we will get used to it. It's a very wise comment. At the same time, I'm still very fascinated by the measurement problem in quantum mechanics. So the measurement problem is a puzzle to me. It's a way you extract information from a quantum system. It's not understood, we just postulate something and it works very, very, very well. So you see, I think we will get used to it, but for me, when I think of a quantum measurement, I'm always a little bit puzzled.
I think it's fair to say that there's no real axiomatic basis of quantum theory. It's very hard to say exactly what it is. So perhaps when we try to say what it is, we'll find that we didn't quite know, and that would be very interesting.
So the measure, I'm sorry.
I wonder whether people would agree with the following statement. Quantum mechanics is actually very bad. And the reason is, suppose you knew the initial state of some configuration exactly. So you have an exactly defined initial state in terms of all the data that you can write down. Then what the quantum prediction still says is the output is a statistical distribution. Where does that statistical distribution come from? There's no answer to such question. To me, that means that there's something completely wrong with quantum mechanics. It only produces statistical configurations. It never produces a Higgs particle exactly where it is. It usually produces some distribution. But distributions are not the reality, at least not to me. So I think that quantum mechanics is just the best thing we have today. Everyone would agree it's a beautiful theory. And I'm not claiming the opposite of that. I'm just saying there's still a beautiful way ahead of us to get a theory that does say that if you produce the initial state with infinite accuracy, you get a final state with infinite accuracy. What you never get is a statistical distribution.
But you probably can't. I don't think you can produce an initial state to arbitrary accuracy.
That's of course a problem.
It will take the infinite amount of time in the universe is only a finite amount of time to put something into a definite value state.
What makes you say an infinite amount of time? Maybe we're lucky and we hit upon the quote-unquote correct theory that's under for all correctly formulated initial conditions tells correctly what happens after. Then that would be equivalent to a classical thing. But I don't see why people would outlaw classical theories a priori. I think that is not correct. We could hope to be lucky to find how all the particles we know interact according to infinitely well-defined laws. Why don't we say that actually quantum mechanics is bad for that reason. Of course, today we don't know how to find those infinitely precise laws, but to deny their existence, I think, is a little too far. They may be there, they should be there, but we don't know even how to start such a problem.
I think instead of philosophical questions, you have to find the experiment to show, you have to find some actual experiment that shows a problem with the interpretation, with quantum mechanics, rather than worrying about the interpretation.
The reason why I say this is that I think all these problems about so-called reality or many worlds, so it's just, to me, it sounds like nonsense. That's why I said quantum mechanics is nonsense. But it just means that no one can never even think that describes reality. A statistical distribution is not real. Particles don't come out in statistical distributions, they come out in very precisely measured positions. And that's very different from the quantum prediction. So in that respect, the quantum theories we have, even though they're much better than nothing, they're still also far away from the ultimate solution.
So I think maybe, I don't know if it's a disagreement or sure, I agree that it's always extremely interesting to have something different which reproduces quantum mechanics, quantum physics actually, not mechanics, is limited, but I think the theories is always theory of something. And so up until you can define, when you say it's this problem with reality or whatever, what do you really mean within the theory? So where does the theory fail in describing those concepts? Unless you have an answer on that, then it becomes a philosophical statement which is ill-defined within the given theory. So therefore, I don't know, for example, there was this mention of measurement issue, but I think this issue, I never understood what this measurement problem means. It's probably my misunderstanding within QFT. Because I think the problem comes when we take limit of non-relativistic quantum mechanics, where you can split the system on a cloud in an observer artificially and the state, but in reality, in quantum theory, there's just one state that it evolves. And so where is the measurement problem? If state evolves unitarily, that's it. That's what you need from quantum QFT.
The issue is reconciling that very general framework with what we experience.
Yeah, but you already answered this question. That's precisely the point. To take the classical limit, what does it mean to have a classical subsystem? You know, it's a coherent state, high population number, a certain subsystem behave classically, and then you can split the system properly. So that's it. But yeah, there is no evidence that it doesn't work. So
Let's hear some.
Yes, I would like to observe that first of everything, we have to consider that we do not have isolated systems. So we have always to consider that we have some sort of dissipation. Then what we need is more than quantum mechanics, quantum field theory, which is not just relativistic, by the way. We apply also to solid-state physics. So, in quantum field theory, we do have infinitely many representations of the canonical or anti-canonical commutation relations. These are phases through which a system which dissipates goes. And this is a beautiful picture we do have today. The only point is that we do not have to insist on unitarity in some abstract way. Otherwise, we cannot have anything which grows or which decays. And what we deal with is always something which grows or that decays.
Well, I don't think anyone was talking proton about that.
Of course, I'm not talking of protons, but I'm talking of a system, a realistic system.
Let me just say that unitarity has been a fantastic guide to the construction of the actual world, and dissipation we can understand as a property of complex systems.
Okay, it will be too long, but it's not so simple.
I'm just going to make a request to all of us who teach quantum mechanics. When the students appear puzzled, don't treat them like idiots, which is what I was made to feel like when I first heard about it at Princeton. And yeah, these are difficult, deep problems, and let's make sure that people understand that and maybe work on it.
So back to the initial assumption, quantum mechanics is fine. Okay, let's accept that. Quantum mechanics is fine, classical theory is fine. Do we agree we have some fuzziness in our understanding quantum to classical transition? Okay, I make the point in a different way. Do we understand we have some fuzziness in understanding quantum to classical transition? Because that's an area which we haven't fully understood. If then, is it a challenge to quantum or classical? I'm okay. I want to point out like discussion about quantum to classical transition, basically, to make it.
It would be good to understand it better, and that's for sure. And what I would love to see, and haven't really seen, is what I mentioned before, a model within quantum mechanics of a recipient observer, so you could sort of point to it and say, yeah, that's me, right? That's my experience of the world. And as far as I know, that doesn't really exist. I don't know if there are fundamental problems in doing it or just technical or severe technical problems, but it would be very interesting to push that through.
There was another question.
So, what do you think of the theory of consciousness of Roger Penrose?
I don't have any opinion. I don't have any thoughts. I don't have any opinion. Roger likes his stuff.
It's not clear to me that consciousness is a fruitful thing to think about. It's too vague. But if you sharpen the question, then we can talk.
Other questions? Maybe then I will ask a question to Gia. You mentioned this idea of this memory burden. When you were talking about it, it came to me, does this apply to more complex systems than the one you were talking about, like neural networks, biological systems? Because the idea seems so general, if it's truly universal, as you say, it should be much wider.
Thanks very much for this question. Yes, regarding neural networks, indeed, since neural networks we can construct, at least theoretically, yes, certainly we can construct neural networks that are close to saturation. Now, the question is whether ordinary biological neural networks are anywhere close to saturation. Not in the direct sense, obviously, because biological neural networks are not really quantum. The classical approximation looks like it works reasonably well. But even if it works, even in classical systems, you can have memory burden effect. So this is universal. The question is whether they are, in certain sense, the biological neural networks could be close to saturation. That's an extremely interesting question, actually.
But do you have an idea about how saturation would manifest itself there? What does it mean technically in this context?
Yeah, so for theoretical neural networks, saturation essentially means the same thing as saturation in the other quantum systems. So what happens is that the excitation gaps, there is an environment created by a system where the excitation gaps of given degrees of freedom, let's call them neurons, collapses to near zero. And correspondingly, they repeat the same story, actually amazingly as black holes. Well, not surprisingly, because the smaller the gap, it's harder to extract information, and then if the system tries to decay, the gap increases, and if there's a memory pattern, then that resists to the decay of the system. So that repeats itself one-to-one. So yes, indeed, it's a universal phenomenon. So basically, every system that is close to saturation of the information storage must exhibit this. Yeah, I mean, so it's actually, I wrote a couple of papers in that direction about neural saturated, but neural networks, I mean, theoretical neural networks. But no, the question is very interesting whether this can apply to biological systems in some way. Thank you.
But where do gaps come from?
No, absolutely. I mean, everything comes, as we just discussed, everything comes from quantum physics, but it depends how we define the degree of freedom in which we store information. Degree of freedom could be a coherent state.
So a quantum neural network.
A quantum would be the one that sort of has really operates with qubits, but if you have, for example, a neural network that operates with qubits, the high occupation numbers, and they can also be written as coherent states, then in a very good approximation, that neural network works classically. I mean, classically means that it will be very hard to create entanglement between the neural states. So it will be effectively classical. So yeah, no, that's perfectly fine. I mean, there's no mystery. And in fact, in neural networks, quantum to classical transition can be really tracked very nicely. So yeah, in this artificial moment.
I think classical neural networks are rather well understood. You can define even complex phenomenon calculation, to mention one thing. When we go to quantum neural networks, I think we'll get a lot of surprise in the next maybe 10 or 15 years. I'm convinced, because the features of a quantum neural network are so different. The role of entanglement is not well understood, and the way you extract information out of a neural network is not understood either. So I think if we would have a quantum computer, these questions would be behind the curtain, but we don't have a quantum computer. So I think quantum neural networks, in my opinion, they will have features that are radically different from the features of classical neural networks.
Well, so you mean the intentional entanglement and stuff, right? Because that's the usual distinction between classical and quantum.
In terms of complexity, they are exponentially complex.
Yeah, because in quantum physics we work with superpositions, and in particular with entanglements, and in classical physics.
I think when you have an exponentially complex, when things are
No, I'm not debating because when I say neural network, this is I have to be very clear. This is quantum field theorists' neural network, because in these discussions I don't care about really algorithms and computation. I care about hardware. So the physical foundations for efficient information storage. This is a very well-defined problem, and there we can trace it very nicely. Yeah, thanks.
I mean, our brain can be compared to a classical neural network. So whatever we understand nowadays can be understood in terms of a classical neural network. It's my opinion. I'm telling you my opinion. Our brain is a classical neural network. You can understand prediction. You can exactly know it. Our brain is not a quantum neural network. So if you have a quantum neural network with 1,000 qubits or 1,000,000 qubits, I think the features are going to be radically different, and you're going to get things that you're not even able to dream about. It's a paradigm that is changing. So it's simply my opinion. I don't want to,
What about temperature?
Temperature, what about temperature?
Is that a question?
It's kind of hot today.
Just because temperature is there, I mean, we cannot forget about non-zero temperature. Thank you.
Yeah. You mean specifically some system, or?
I mean that you have to do with something which is not always there, and perhaps it's quite good that we are so far from understanding the real things, because it's better at this moment of wars ignorance, because knowing more will mean worse war.
I don't know, maybe this was so regarding temperature, so again, I mean, I fully agree that it's always good to know more and things, but I mean, when I don't know if it was connected with the saturation, but when I talk about saturation, it's a very well-defined system and very well-defined feature. And indeed, for example, if you have a saturated system, when the saturated system decays, I said this during my talk, it appears that the decay products, they are approximately thermal. They obey thermal distribution. This is a feature of saturation there. So I don't know whether this is what you mean.
I was not referring to saturation. I was referring to the general problem of dissipation. That is a general problem. How do you deal with in one single representation? You do not have finite temperature quantum field theory as far as just excluding some example.
Yeah, I mean, my answer would be that every time, so if we define the problem, if the problem is well defined, under what do we mean? This, for example, you said quantum field theory. I mean, thermal quantum field theory, we know how to deal with it, but it's an idealization. It's an idealization. You have to have a thermal equilibrium, and so on and so on. Formally, sometimes it means that you have to wait infinite time before system. So it's always an idealization. Of course, it's never exact. Obviously, there are always non-thermal fluctuations, even in real systems. In this room, there is a temperature, but there are huge non-thermal fluctuations and stuff. So yeah, I mean,
I guess if we're in equilibrium with that.
I mean, there have been some very delicate and brilliant experiments done in quantum thermometry and quantum refrigeration, and so no significant problem has emerged as far as I know. It's just another aspect of understanding the consequences of quantum theory. So it hasn't been necessary to introduce anything essentially new as far as I know.
Maybe we can leave this room.
Okay, so I got a question for Professor Dvali about so at the end of your talk you mentioned the implications on the pseudo universe, both early and late universe, etc. So this idea of saturation and what are, this might be a naive question, what are like the direct consequences that it would have on both the early and the late pseudo universe in terms of like the observable quantities and just in general think of the universe?
yeah, thanks. That's a great question. I don't know the answer. I must say right away. Okay, there are some sort of feelings about. I can share my feelings. So first of all, of course, the fact that the sitter is a saturated state, that simply follows from the I'm relying on Gibbons-Hoffman entropy. Okay, so if I take this as granted, and there is an evidence from the construction that I gave, explicit construction in string theory, how this entropy emerges. Yeah, if we take that, then there are memory modes. You see, if system has entropy, huge microspace entropy, then there are memory modes, and correspondingly, there must be some sort of a memory burden effect. So the way I would envisage this, and actually we even wrote a paper with collaborators of mine. If we think of Gibbons-Hawking radiation as a depletion of the master mode in this, then it has to gradually create gap of these memory modes, and this memory mode should be created. And this presumably should be imprinted in the microwave background spectrum and stuff like this. Therefore, this probably will depend on the duration of inflation. So if inflation lasts very short, then probably this imprint will not be significant. But if inflation lasted sufficiently long, then memory burden should be somehow visible. Now, where should it be visible? Well, in higher order correlators. Now, how to precisely translate to make this prediction, of course, this requires some study. So, yeah, but I think, yeah, that's the way I would envisage this imprint of the memory burden.
And the memory burden, it will be there, as I said, like
like a fact, right?
Well, I mean, again, I mean, facts are, so I cannot envisage, and I encourage everyone to come up with a counterexample of a Hamiltonian. So if there is some sort of a Hamiltonian in quantum physics that governs this evolution, I cannot envisage any Hamiltonian that has this ability of the saturation and is not exhibiting the memory burden. So the memory burden goes hand in hand with saturation. So therefore, yeah, this is a conjecture or expectation, but yes, I think something like this should be happening.
So if inflation lasts long enough, those inputs would be.
I would think so. Yes, of course. But this is at the level of the feeling now. It's not backed up by any rigorous high-order correlator calculation. So, yeah. Thank you.
Maybe we should take one last question and then we're ready to continue at lunchtime.
I have a question to Professor Frank. You mentioned in your talk that QCD has a challenge, which is equation of state of neutron stars. So, what would be the best route to progress in that direction? Because especially you mentioned axion, and I'm having in mind the QCD axion, although there are so many axions proposed.
There's only one correct axiom.
Yeah.
But well, there are many things that are called axiom, but the concept of axion that leads to a solution of this problem of T-symmetry and gives the dark matter, that's almost unique. But anyway, what's your question?
My question is how it can help to make some prediction about equation of state of neutron stars.
Well, axioms don't help you at all with the equation of state of neutron stars.
Yeah.
Well, let me compare the problem of ordinary stars. With ordinary stars, we have a very rich and detailed theory of their inner structure based on quantum electrodynamics and nuclear physics. For neutron stars, we know the equations, I think with high confidence. They are the equations of the standard model, and especially QCD, but we don't know how to solve them with sufficient accuracy. In QCD, we have very powerful methods for certain problems based on lattice-Gibbs theory that nowadays give remarkably precise answers for hadron masses and a few other things. But they break down at finite density for what you might say are technical reasons, but they're severe, such severe technical issues that I think they become conceptual. The famous sign problem, or even gets worse, it's a phase problem. We can't use the same techniques that are successful for calculating masses and other things. I would like to think that that's a problem that some very clever person will make progress on, but it's been quite a few years and nobody has. Maybe just better computer hardware, maybe quantum computers could make a difference here, but it's a completely open challenge. And it's kind of a scandal that we don't have we know the equations, but we can't solve them even semi-quantitatively to do justice to neutron stars. And that's becoming serious because with the gravitational wave detectors, we can get some access to the interior of neutron stars. So experiments coming for which, and observations are coming for which the theory is inadequate.
Okay, maybe we should close the discussion now and go to lunch. So,